Hi everyone, I'm László from Luxembourg, and I'll be speaking about how we migrated from our OpenWayback playback system to a hybrid between PyWayback and SolrWayback with a special S3 storage. Hi. Okay, so many of you might recognize this. So that's OpenWayback, and this was our search interface a few months ago. And as you can see, it's not really ergonomic, difficult to search in our web archives, and especially difficult to find what you're looking for. And so we decided to change that. So in the beginning, everything was hosted on a single machine. 8 CPUs, 24 gigs of RAM, and everything, all our data and metadata was just hosted on a single mounted disk, which wasn't ideal, to say the least. And so, other than hardware concerns, we had a lot of software concerns, and obviously whenever we wanted to add some new files to our collections, then we had to force a server salvage because we had to restart our Tomcat server. So it was quite an inefficient design in itself. So I've included a picture of a typical Luxembourgish searcher in our web archives. So we wanted to change that, and what we did is that we invested in 4 new high-end servers, and we made a strategic decision to migrate all of our work files onto S3 storage because our governmental IT provider had just installed this solution, and benchmarks gave favorable results compared to NFS. So we copied our files there, and then obviously after that we migrated our software as well to the PyWayback and Outback CDX frontend, and SolrWayback for searching full text, which is not yet rolled out, but will be in a few months. Right, so here's a little comparison of the before and after. So as you can see, the after looks much better than the before. So we have 3 terabytes of RAM going on there, and almost 200 CPUs. So that, I think that should be enough for now. Right, I've already talked about this. Okay, so in terms of storage, so some of you might know what S3 is. So it's a different storage paradigm than conventional file and directory-based storage. So basically, you identify your object with a key, and then you access that key in a different way, and that allows you to have better performance compared to NFS. At least that's what we see. So yeah. However, obviously, storing all our works in S3 has its own challenges because we need to find them. So we need to set up a database to be able to map each file to their S3 object storage key. Obviously, PyWayback cannot read from an IBM-based S3 storage. It can, based on AWS storage, but not IBM. Those two are practically the same. However, IBM has implemented some improvements, which it would be good to take advantage of. And we need to be able to communicate with our own internal governmental S3 endpoints. And then, of course, yeah, we had to copy 340 terabytes of works to S3. So that didn't just happen by copy pasting from an Explorer window to another. So right, how did we store the paths of our works? So as I said before, whereas in NFS storage you can have /mnt/my folder/my work. That's not the case with S3 storage. So we set up a database to map our files, and a small REST API to access that database, and integrate it with our existing software solutions. So this is just a little example. Probably you can't see much, but a row in that database for our work files would look like this. So each work file has an ID, it has a file name, some metadata, and then we have an S3 path, which is the name of the S3 bucket in which we store our file. So a bucket is kind of like a folder, but it isn't. It's a slightly different paradigm, but anyway, it enables us to have a centralized place per collection. So we have a bucket per collection. So in this case, this work file here was stored in our Win2Crawl 2019 bucket. And then we have some other metadata like the crawl organization and crawl technology that was used to harvest that file. Right, and then onto PyWayback, because we need to we had to modify PyWayback to be able to read from our storage. So PyWayback is already able to read from S3, but only AWS technology. So that we had to change. We had to load it from our bucket, the work data that is, connect to our custom endpoint, and obviously know where the work is. So we had to get that path from the DB. Right, so we developed this small IBM S3 module in PyWayback using the IBM Boto 3 Python module, which is really almost the same as the existing Boto 3 already used in PyWayback. And the way we implemented our workflow is that we implemented a new loader class, extending base loader. And the point is that using this solution, so as you can see here on the bottom, you have our BnL loader, Bibliothèque Nationale de Luxembourg, so National Library of Luxembourg's loader. And the point is that you reference this in the config file here in the archive paths key. So the value here is the BnL colon / and then our database API's URL, so that we can get the path of our work file and then get the data from the S3 bucket. Sorry if I'm going too fast, just tell me if you have any questions. Right, so here you can see a wall of text. So what we did, so in summary, the workflow that we implemented in PyWayback, so every single time that PyWayback needs to load work data, the BnL loaders BnL loader is instantiated, and then we load it from the load method. Then we connect to our MariaDB database to get the S3 bucket where we have stored the work file. And then we use that path together with the offset and length where we want to fetch the data, which is provided by Outback CDX, as I mentioned earlier, to make a call to our S3 cluster internally. And now PyWayback has all the data to load the page. Right, so this is a little simplified version of what's going on. So some person goes to a terminal in our reading room, connects to our playback engine powered by PyWayback, and with an Outback CDX index server, so gets the CDX data from there and the name of the work to load. And having that information, we use that to get the name of the S3 bucket in which we have our file physically, and we then use that data together with the offset to get our data. So in green is everything that we have implemented inside PyWayback that did not exist before, and then the orange is something that already exists, of course, in PyWayback. Okay, so this is how it looks like now today. Our web archive portal. This is just using the PyWayback's templating engine, which is a really good way to customize your landing page on PyWayback. So we've split our web archives into two different sub-collections. Everything that's freely accessible doesn't require a login or a paywall or things like that. And then everything that we harvested behind the paywall is accessible with a separate sub-collection. We spoke about that yesterday with Anders and our other colleagues. Right, SolrWayback now. So we're in the process of implementing full text search with SolrWayback, and our idea is that SolrWayback will be used as the main search portal, however, the playback itself will be made with PyWayback, and so we'll use the alternative playback option of SolrWayback to forward the user to PyWayback. Alternatively, Thomas has provided a new feature where we can use PyWayback as the main playback solution. So we're going to make a proof of concept about that. And yeah, like all the problems that I've talked about with PyWayback exist also in SolrWayback. Obviously, these are not problems, but these are just features that we need to add. So let's see what we needed to implement there. So obviously, for our workflow, we need to get data from our S3 buckets, and so we need to contact our database to find out the S3 bucket. Yes, sorry. Yes, 3 minutes.
No, for if you leave 5 minutes for
Yes, I was there. Sure. Thank you. Then, right, we need to load the data from S3, obviously. And we have some special considerations in Luxembourg because we need to detect not safe for work content in works. We cannot show anything that's gory or violent or nudity in our reading room. And we also need to detect viruses. So if we index 340 terabytes, then let's do it in a way that we can detect viruses. Right, so SolrWayback uses resolver classes to resolve org files and get data from work files. So we developed our own, which is a BnL org resolver, and the main challenge here was to be able to skip directly in the data stream when we get the data from an S3 storage to get to the correct offset, because if you have a 1 gigabyte work file, for example, and you need a 900 megabyte, you don't want to load 900 megabytes before that. So you need to do some stream skipping there. And here's an example of what we implemented in SolrWayback. So as you can see, the first point is getting the file name, just the file name, no paths, because SolrWayback indexes the work files in such a way that you have the full path where you index the file from. And then we use that to contact our Web Archive database API service to get the bucket. And then we return a skipping S3 input stream, which is basically a fancy way to just get the data from the correct offset. Right, running short, so I'll just try to speed things up. So for the not safe for work and virus filter, so we developed a small application. This will allow us during indexing to detect any not safe for work content inside work files. Obviously, we will make that available open source on GitHub, and it will also be able to detect viruses. Some cool features. So you can either run it in test mode statically, so you can just give it a work file on the command line that will just return your work resources, and will say for each of those resources whether they're virus or whether they're safe or not safe for work. So for the latter, we've used an artificial intelligence that gives a score between 0 and 1 for each resource in a work. 0 meaning completely fine, and 1 is you should probably not show that to the user. Here's an example of how that works. So this is a curated work file that we've just specially made for this. So this is a command line output that you will get as well when you run the file, the program on a work file. And now here's one from our production. So as you can see, there are some work files where you have a lot of undesired content. So we've even color coded that for you if it's might be visually more interesting. Now, how do we use this? And this is really the last thing. So. So we cloned the UK Web Archives work indexer for that, and the point is that we implemented a workflow in there to contact our not safe for work and virus filter application, because it exposes a small REST API that you can just use to send the path to a work file, and it will return whether it's safe or not safe, or is it a virus using some JSON encoding. So. Using that, we were able to insert some more fields into our Solr schema. So as you can see, these are the 3 new fields that we've implemented there. Quite simple: is virus true or false? And then the not safe for work probability, which is a number between 0 and 1. And then is not safe for work, which we just made there so that we can speed up the process on the front end. So we can just quickly show or not show something and obviously you can fine tune what not safe for work means for your organization. And some final words. So this indexing process will take about 4 weeks on these approximately 200 CPUs. And we'll use WABAC's alternative playback option to redirect to PyWayback, or alternatively the main playback option. So we'll see what we will do there. And in a few months we'll be in production, and I'll be more than happy to share the results of that. And here are some cool links if someone wants to take a look. And any questions?
Thank you.